Okay, we're going to go on to chapter 5 now. This is going to be where we're going to get into chemical reactions. Please do make sure you actually practice the previous stuff. Oh no. Yes. 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 So it's okay. I don't know if we have to do notes or something. I have no idea what I'm doing at high school. This is the first time I've ever been in high school. Okay. Yeah, I think we operate kind of like college most of the time in this wing, or at least their expectations of professors and such that they know we don't know anything about high school. Okay. First thing we're going to talk about is thermodynamics. Nutritional labels list the number of capital C calories. You all have seen that, hopefully. Capital C calories on nutritional labels. Very good. They also typically list kilojoules. Has everybody seen a kilojoules on a label before? No? Okay. It depends on the country whether they do that or not. If it's an international product they're planning on selling everywhere, they'll do it. Okay. So this is actually a measurement of the amount of energy content of that food. And so that's actually the amount of energy that would be released if you burn that food. Okay? We do harvest most of that energy biologically, but sometimes we don't harvest the entire. Okay? It's actually a not entirely accurate. It depends on the person, in fact. Understanding how energy and heat are exchanged in chemical reaction actually describes the area of chemistry we refer to as thermodynamics. Literally thermo heat, right? Dynamics, how things change. Okay? Now, when you eat, the food molecules are going to be broken down. They actually aren't broken down much by the acid, but by the enzymes in your digestive system, part of which exists in your stomach and saliva, and start working on it. Did you guys know that you start digesting sugar as soon as you get into your mouth? Okay. If you just touch sugar water, is it sticky? Just the sugar water? No. No, if you just touch sugar water, touch soda, it's not sticky. Like if you just go soda, dink, it's not sticky. Why does it become sticky? Not the evaporation. Just sugar alone isn't sticky either, is it? So the sugar becomes sticky because of your saliva. You just happen to spread your saliva all around your mouth and fingers all the time. So people don't realize it, but everything around you is kind of covered in a very small amount of saliva. Okay? And that saliva has an enzyme that breaks down sugars, and that's the tacky sensation you feel when you have sugar water on your fingers. Okay? If you didn't get any saliva on it, it does not get tacky. Okay? It's when it breaks down. Now, if you leave the sugar water there long enough, it will oxidize and get tacky. And that's why, leaving it on the desk and it starts breaking down. Okay, so the study of the pace or rate of a chemical reaction, this is going to be called reaction kinetics. Kinetics being how fast something happens. Okay? And so reaction, how fast reaction happens. Notice these are very different concepts, thermodynamics and reaction kinetics. One tells you if something will happen spontaneously. The other one tells you how fast it happens. Okay? Let me give an example that you probably know better. Okay, would the gasoline in your car burn? Yes. So why does your car not just spontaneously go boom? There's no fire. What happens though if you leave a tank of gasoline just sitting around? Can you use it after about a year? Anybody know? It's not evaporation that'll cause you to have bombs. So what happens is the oxygen actually does react with the gasoline in your tank. And it will slowly gel the gasoline in your tank. So if you ever get a very old vehicle that hasn't run for a while, what will happen is if you try to run it without flushing that gasoline out, you'll actually clog up the entire inner workings. And it'll basically destroy the engine. You have to take it back apart, clean every bit. It's awful. So you actually cannot keep gasoline in a tank and expect it to be okay. And that's because it does oxidize. It actually does react with the air. Okay? It just does it really slowly. And so when you add a spark to it, it does it a lot faster. And that makes it a lot more explosive, right? Okay. And so that is actually the difference between thermodynamics. It is spontaneously react with air, yeah. And kinetics, right? Slow kinetics just slowly oxidizes, not a huge deal over the course of like 6 months. Versus we give it a spark, goes really fast, kaboom, right? Okay. All right, so chapter 1 actually defined energy as the capacity to do work. Chemical reactions involve an exchange of energy between substances with energy dissipated in some reactions and transform potential energy into kinetic energy or vice versa in other reactions. Keep in mind, when I talk about potential energy, that's like a rock sitting on a hill, right? And then when it starts moving, that's going to be kinetic energy, right? When I talk about reactions, the form of kinetic energy we're most often going to be referring to is heat, okay? That's the majority of kinetic energy in reactions, okay? So remember that when reading chemical reactions, the reaction always appears on the left to the right. So the reactants will be on the left, products on the right, and we'll get the yields, which is this arrow right here, in between them. That yields is a directional equal sign, right? Okay. Everybody good with that so far? Fantastic. Okay, so let's talk about the heat of the reaction. Now, has anybody ever heard of exothermic? Yeah, it gets bantered quite a bit actually in media and around you. So this is going to be a reaction that gives off heat. Exo meaning out, right? And then thermic is heat. Okay? And so it gives out heat. It puts heat into the outside, out of the reaction. Endothermic, on the other hand, endo means in, thermic means heat, right? And so in an endothermic reaction, heat flows inward. Okay? You've all seen an exothermic reaction. That's going to be burning gasoline, right? Burning coal. Those are all exothermic reactions. The reaction's taking place. Heat is radiating out of the reaction. Okay. Endothermic reactions. Has anybody ever used one of those cold packs that you break them and they get cold? Yeah. That's an endothermic reaction. Okay. You may have also experienced it if you took like a bunch of salt and then dissolved it. Certain types of salt will actually cause endothermic reactions. It's actually how a heat pack works, by the way. You dissolve a certain salt, and the reaction of it dissolving creates an endothermic. But that will actually cause you to get colder because it's drawing heat from you. Okay? So the reaction draws in heat. This is actually an example of that. See, heat's over on the reactant side. So it's getting drawn into the reaction. Okay? This one here has heat coming out as a product, and so that's an exothermic reaction. Mm-hmm. No. It can be, you could have a solid going aqueous and giving out heat. Yeah. This happens a lot if you ever dissolve KOH or NaOH. It'll get really hot. So, in fact, it'll melt the container of plastic.
What does aqueous mean? Like
dissolving in water.
Oh.
Mm-hmm. So this one right here is a solid salt that you're dissolving in water. This is ammonium nitrate, by the way, oftentimes used in things like explosives. But you can also dissolve it and soak like wicks in it. And that's how you can make the wrappings for like a firework. Yeah. That starts the reaction. And so this would be the solid salt dissolving in water. And this one right here is actually the aqueous, and then we're actually causing it to precipitate out into the solid right here. Okay, let's talk about change in enthalpy. So we can think of the exchange of heat energy in a chemical reaction as a more general thermodynamic term, which is going to be change in enthalpy. Enthalpy is going to be heat change, but with constant pressure. Okay? So we're not considering pressure in this. It makes it a little simpler when we're doing the math. Most systems that you would have to deal with would not build up pressure because you don't isolate the system and you allow the pressure to go out to the rest of the atmosphere. Okay? And so enthalpy usually works very nicely. Change is this capital delta here. That's that triangle. And then this right here is the symbol for enthalpy, which is H. Okay? Okay, so in an exothermic reaction, what we're going to see is this change in enthalpy. This is going to be a negative number because our system, our reaction, is losing energy. It's losing heat. That's the heat you feel that's coming out, right? Okay, so in an endothermic reaction, this is going to give us higher energy. It's going to pull energy into our system, into our reaction. And so that delta H is going to be a positive number. You can actually sum up this same thing I just told you with these symbols here, which is the delta H of the overall reaction equals the delta H of our products minus the delta H of reactants. If this number is bigger than this one, we have an exothermic reaction. This one's smaller than this one, we have an endothermic reaction. Okay? All right, so let's talk about entropy. Whoops, I need to change that. Again, entropy, not enthalpy, okay? That's what happens when you copy and paste. Because that symbol is a pain to write on PowerPoint. Okay, so again, this is going to be a change in entropy. Most people are going to call this randomness in a system, okay? There are better definitions, but that one works fine for you all. Do you guys want the better definition? Okay. It's the number of options that a system has. So think of it a bit like this. If I took away desks, you guys have less options to sit in, right? And we would refer to those in chemistry as microstates, possible states you could be in. Okay? The more microstates or possible states you can be in, the greater the entropy. The less you can be in, the less the entropy. Okay? I can't hear you over this. Sorry. Yeah, my definition is the actual definition of entropy. Yeah. This book uses, usually what you do when you're teaching this is you basically, you know the 5 states of teaching? Where you go from like explaining it to a kindergartner, explaining it a little bit more complex. Yeah. This would be considered that initial state of explaining, which is randomness. Yeah. But the microstate explanation is like the 3rd level. Yeah. Does that make sense? It's actually saying the same thing because that's what randomness is supposed to be. But randomness is such a random word, right? Yeah. It has a lot of meanings and context. So, yeah, when you're thinking of it, definitely think of it as the microstates. It's a better definition. Yeah. But that's what actually randomness is supposed to be. People just don't realize that. Randomness is the number of options you can have. Okay. And so this is oftentimes referred to as paying the piper, by the way, because all processes in the universe are spontaneous only if they increase the entropy of the universe. Okay? So everything in the universe drives towards more options or more spontaneity or more entropy. Okay? Yeah. So if you have a positive entropy, the entropy is going to be positive, it's going to increase, and you're going to have the process being driven forwards, and that will be spontaneous. If you have a delta S that's negative, then your entropy decreases, and so that process is not going to be spontaneous in terms of entropy. Okay, we need one more concept. Notice that I've given you entropy, I've given you enthalpy, right? We need a bridge for those things to work together. Okay? And this right here is going to be that bridge. This is going to be sort of the sum of those two components. Okay? So what I want you to have in your head is this framework. Whether something happens or not spontaneously is going to depend on the free energy. Okay, this is called Gibbs free energy, delta G, right? Now, when this number here is negative, you're going to have something that happens spontaneously, right? That's going to be a spontaneous process. For example, is the rock going to roll down the hill? Well, that's going to spontaneously happen, isn't it? Okay. The reason it happens spontaneously is because its Gibbs free energy is negative. Okay. Now, what if you have something that doesn't happen spontaneously, like the rock being pushed up the hill? What's Gibbs free energy would that be? It'd be positive, yeah. So what that means is when you have a positive Gibbs free energy, it will not happen spontaneously. You have to put energy into it to make it happen. Okay? And that also means that its opposite direction is spontaneous. So if you look at the rock example, as we're pushing the rock up the hill, what if we just stop giving any energy to it? We just walk away. What happens to the rock? It rolls back down on us, doesn't it? Because it's spontaneous in the opposite direction. Okay? Okay. Anybody want to guess what happens if Gibbs free energy is 0? Yeah, nothing. You can say they're both spontaneous or they're both non-spontaneous. Okay? So it'll spontaneously happen in both directions or neither direction. One, two. But you will have no overall spontaneous structure. Mm-hmm. Exactly. This would be like the rock just resting and there's no hill. It doesn't spontaneously do anything, right? Because the next position over is not energetically favorable. Okay? Can it be moved? Yeah, if you give it a bit of energy, you can move it, can't you? But it's not going to spontaneously do anything. And if you give it a bit of energy, it's not going to spontaneously go back. Okay, this right here is the formula of how you take those two parts I gave you and put them together. Okay, and so this is going to be delta H. This is going to be the enthalpy. So that's whether it releases heat or takes in heat. Notice you already knew that things that were gave out heat typically were going to be spontaneous, weren't they? Yeah, like burning fire. If you start burning gasoline, is it just going to like stop once you stop providing a spark? It's going to keep going because that's spontaneous. This right here, notice that T right there is the temperature. Now this has to be in Kelvin, okay? Very important it's in Kelvin, not degrees. So degrees will never function in this formula. You'll have lots of problems, Kelvin. Because at absolute 0 here, this term actually drops out, okay? And that's because everything's frozen in place. You can't have entropy. You can't have different microstates if you freeze everything in place, right? Okay? Like, for example, think of your cells. There's all these deaths in here, right? So the number of microstates you could be, the number of possible states you could exist in, when you're all moving around is a lot, right? When you're all sat down like this, well, we froze it into one state, didn't we? And so now there is no entropy. We're frozen. Okay? Is that making some sense? Yeah. Things have to actually like have a possibility of rearranging or there to be entropy. If they're frozen completely in place, your entropy's gone. Okay. Okay. Does everybody remember what temperature is, by the way, in heat? It's randomized kinetic energy. Okay. Okay, now there are actually terms. Remember how we had exothermic, endothermic before? Okay. Well, thermic was referring to the enthalpy. Okay. And so there's actually terms for Gibbs free energy and the entropy as well, for referring to those. Now, the Gibbs free energy one is going to be the most important for you, and it's going to be exergonic. That means it gives off energy, and endergonic, that requires energy put in. Okay? And this is where we're going into the negative, right? Gives off energy, negative delta G, exergonic. Okay? Gives out energy. Endergonic takes energy in. Okay, so we talked about spontaneous process. It's going to continue to occur once started. It does not require the energy from the surroundings and will just continuously occur. Now, does this say anything about the speed? Not at all, does it? Not at all. And so, yes, the rock will eventually fall off down the hill, right? And yet there are rocks that have been on top of the hill for 1,000,000 years, right? So it will happen. It may not be fast, but it will happen eventually, right? And for example, the Grand Canyon is always a great example of this. That was always going to happen. That was a spontaneous process. Okay? Didn't happen fast, though, did it? Happened over the course of hundreds of millions of years. Okay? And so again, kinetics is how fast it happens. We're doing thermodynamics. Is it going to happen spontaneously? Okay. So one of the ways you can think about this, was anybody having trouble envisioning this in their head? No? Okay. Okay. This is another way to think about it. You can think about like the stream, right? So if you have a delta G that's positive, this is like paddling up the stream. If you stop paddling, you're going to start going back. Right? If you have a negative delta G, this is going to be like going with the stream. Okay? Like you could have your anchor down and not yet go, but once you get your anchor going, you start it forward, you're going to go spontaneously. You don't need paddling. Okay? Okay, so this right here is your thermodynamics in terms of an energy chart. Okay? So what we have here is we have the G of the reactants, the Gibbs free energy for reactants. Here we have the Gibbs free energy of products. And what you'll see is that when we do this reaction, we release potential energy and transform it into a form of kinetic energy, which is heat energy. Okay? And that's this release right here. And that gives us the negative delta G. This could be entropy, this could be enthalpy, right? We're not specifying in this case. Okay? And in case any of you are wondering, yes, entropy does drive things forward. Entropy really does is energy that you can do work with and transform things with. Okay? Entropy is why most of the process of like, if you drop a dye in a liquid, what happens? It spreads out through the liquid, right? Most of that energy is actually entropy. Okay? There's a number of different gates in your cell membranes that actually function due to entropy energy, actually, not through enthalpy. And so they take in molecules through those due to entropy. Huh? That's the number of microstates, the randomness. Okay. Okay. Now, this one right here is an endergonic reaction. And so what you'll see is the reactants have less potential energy than the products. And so you had to take in energy to get it to a higher potential energy, just like you lift a rock and put it up on a shelf, right? You're putting energy in, it has potential energy, it gets knocked off, it's going to come down and boom, right? Release that potential. Okay. All right. Now, living systems free energy is the energy that can do work under cellular conditions. During a spontaneous change, the free energy decreases, the stability of the system is going to increase. And so what you are as a living being is every moment of living, you're doing breathing, you're doing cellular respiration, you're doing all these processes, right? And all these processes' purposes is literally to bump your potential energy up and keep it elevated so that you continuously fall downwards towards more stable states. Okay? And that's how you live. That's how you keep doing things. So you continuously are taking in oxygen, taking in nutrients, so that you can increase your potential energy. And then as you live, you fall down to that delta G equals 0. Okay? Okay. Now, now the living energy systems, the free energy given off in one chemical reaction is going to be coupled to input to another chemical reaction. And so we'll have these chains of reactions, or cycles typically, where we're going to have something that's spontaneous coupled into other stuff that is not spontaneous. Okay? And so what you do is you knock it up, make it spontaneous, make it high energy. And then you're going to transform it and lose energy in those steps. Yeah. You're providing those activation energies, but in a very unique way. Because you can't just put in heat. Like if you just continuously try to put in heat in your body, you would die, right? Destroy your structure. So, in the biological systems, we do it with typically ATP. So the main molecule that transfers energy in living systems, this is the adenosine triphosphate. Remember the phosphate groups we've been talking about? Yeah. And so this is ATP. This is going to be that source of G, that source of energy you're putting in. Okay? So that you can then take non-spontaneous processes and get them moving and going. Okay. And so right here, we actually have a spontaneously exergonic reaction, which is taking these nutrients like sugars, fats, and then breaking them down. Okay. And then we get ATP from them. And then that ATP is going to be used to power non-spontaneous endergonic processes, right? Like walking, eating, doing all those things. Okay? Okay. And we make a complete cycle out of it. Okay, so let's talk about activation energy. Okay? Now, activation energy is going to be related to kinetics, ultimately, right? It's what you have to do to get that thermodynamics started, okay? And to get that moving. So think of the boulder again, right? We have the boulder, it's resting on top of the hill. Well, it doesn't usually just roll off, it can sit there for a while, right? Eventually it will roll off, but it can sit for a while. And so that first push, that little bit of energy that's needed to get it going, that's going to be activation energy, okay? Now, if your process is spontaneous, you will recover that energy in the reaction, okay? So for example, this right here is an exergonic reaction. So again, the reactants are higher potential energy than the products, like our boulder, right? And the reason they don't roll forward right away is because of this right here, which is the activation energy. It's the hill you have to overcome first. It's the amount of energy you have to do to get it started. It's the spark that lit the fire, okay? Once you have the process started, though, it's going to continue going on its own because it's giving off energy in this process. Okay? And so that would be like the fire, right? So if we light the fire, we have to use the spark. That's the activation energy, okay? And then once we have the fire lit, it burns, right? And so it puts out that energy right here. That's going to be your negative delta G, right? That energy is then going to cause other gasoline molecules to also overcome their activation energy barrier, okay? Which is why once you light a spark, the fire spontaneously burns very quickly, doesn't it? Okay? Because you're overcoming this activation energy. Now, let's think of a little thought experiment, okay? Does anybody even walk to school at all? Is that even a thing? No? Yeah. Do you guys walk anywhere? More than a block? Yeah, okay. Okay, so do you ever walk where there's a hill? Okay, fantastic. Okay, so you walk over a small hill, like a speed bump, okay? Is that going to take you more time? A little bit, but not much, right? Maybe like a microsecond or something. So what if I took that hill and I start just increasing that hill? I keep dumping more and more stuff in there, and I get a Mount Everest. Is that walk going to take the same amount of time anymore? No, it's going to be a lot longer, right? Yeah. And so that is actually a great allegory for activation energy. If you increase that activation energy to a very large amount, reactions get really slow. If you decrease that activation energy, reaction get much faster. Okay? And so it allows your reaction to go much faster. This right here is an endergonic reaction. This would be your activation energy right here. That difference between the top of the hill and where you start from. Okay? And see how big that hill is now? So this is going to take a lot of energy to get started, right? Okay. It's also going to take continuous input of energy because it's non-spontaneous. So we're going to have to just continuously put energy into this if we want it to go. Okay. That making sense for everybody? Okay. Yeah. We cover so broad of a range of materials that this course is like some people get certain chapters, some people don't get them as well. And you just kind of have to do your best with chapters that are harder, seek out help, and then you turn around and the next chapter is easy for you. Yeah. Yeah. Don't forget though, please do come in for help if you want to.
Yeah. I know how to use the thing already. But we didn't want me to help with stuff.
Very good. Yeah. Did you see the flyers for tutoring?
Yeah.